Okay, so the last two lectures we talked about separation of variables and went through all the steps required to do a separation of variables problem. The problem that we looked at was actually a pretty simple one. I've shown it here. It's simple because the boundary conditions are pretty simple, right? So we had a zero temperature here, we had no heat flux on these two edges, and the only non-homogeneous boundary condition was this top one, right? So that gave us this math problem, I guess, over here, and it really sort of lent itself to solving with separation of variables because first of all, it was just already in a form that would allow us to apply separation of variables, right? We went through step one, which was check that your problem meets the requirements for separation of variables. The PDE is homogeneous, and then we had both boundary conditions in one direction, the x direction, were homogeneous. So we didn't have to do anything. In fact, one of the boundary conditions in the y direction was homogeneous as well, which made it particularly simple. So today we're going to talk a little bit about what you do when you encounter a problem where it's not so easy just to get started, right? And basically go through some, slightly more advanced things you can do with separation of variables that will allow you to actually tackle, more real-world problems. Because no real problem that you're going to come upon is going to be this simple, right? It's not going to have 3 of the 4 boundaries homogeneous, and you just have to be able to understand how to break apart a real problem or transform a real problem into a problem that you can solve with separation of variables. Okay, so here's a more realistic problem. This is the problem we solved. It had these very simple boundaries. Our problem that we're going to look at today is a little bit more interesting. This temperature over here is no longer 0, because obviously 0 is only ever just sort of a reference temperature. It's T infinity, and then this boundary over here convex to T infinity. So this boundary is set to T infinity. That's the temperature. So that would be what you would get if you had a really high heat transfer coefficient over here. And then over here we have a finite heat transfer coefficient, so this boundary convex to T infinity. And down here, instead of being adiabatic on the bottom, we have a specified heat flux. So a little more interesting. The steps are the same, it's just that you have to be kind of careful. If we were to derive the differential equation for this problem and the boundary conditions, we'd see that we couldn't use separation of variables as it stands. So let's start by deriving the boundary conditions. The boundary conditions on the left side and the top are really easy. They're just set temperatures. So the temperature at x equals 0, so along this line here, is going to be T infinity. The temperature at y equals along this line here is going to be TH. On this side and this side, we don't know the temperature, right? So we end up having to do an interface energy balance. That's what we always end up doing when we don't know the temperature. We have to make sure energy is conserved. So if I do an interface energy balance on a differential area on the right side, so here I have a boundary that's just inside of that right boundary. Here I have a control surface that's just outside of that right boundary. On the inside control surface, I have conduction. I've drawn the arrow in the positive x direction, so this is going to be minus k dt dx at x equal w. And then on the outside of that, I have convection, right? And the way I've drawn the arrow is going to be h bar times the temperature of the boundary minus the temperature of the fluid. So T at x equals w minus T infinity. So in equals out. You never have any stored energy in one of these interface energy balances because they're infinitesimally small. So conduction has to equal convection. So that's the boundary condition over here. Down here I do the same thing, right? I have a control surface that I'm going to put just inside this boundary, so just above the bottom surface, and the control surface that I put just outside the boundary. The heat flux is going into this, and then coming out of it is minus k dt dy at y equals 0. right? That's just the direction I drew my arrow is in the positive y direction. So that's what Fourier's law says. So in equals out. So q dot double prime is minus k dt dy at y equals 0. So my math problem then is this one right here. Right? I have the same differential equation inside the computational domain. Right? Me changing the boundary conditions didn't change that differential equation. The boundary conditions are a little different though. At x equals 0, I have t infinity. That's this guy here. At x equals w, over here I have conduction has to equal convection. At y equals 0, so down here I have the heat flux coming in has to equal conduction. And then at the top I have a specified temperature. So the temperature at y equals h is th. So, you know, if I was to go through the process of solving this new problem with separation of variables, I'd still start with step 1. And step 1 says, check that your problem meets the requirements for separation of variables. So I have to have a partial differential equation that's homogeneous. This partial differential equation is still homogeneous, but I have to have both of the boundary conditions in one of these two directions. So either these two or these two, both boundary conditions must be homogeneous. And you can see that the boundary conditions in the x direction, neither one of these are homogeneous. And actually the boundary condition in the y direction, neither one of these are homogeneous. So none of these boundary conditions are homogeneous. So one thing I can do is what's called superposition. And what that is just breaking this apart into two problems. One that deals with the non-homogeneous boundary conditions in the x direction, and the other that deals with the non-homogeneous boundary conditions in the y direction. And we'll talk about that at the end of this lecture. But an easier thing that I can do is recognize that I can always solve a problem relative to some reference temperature. So basically, instead of solving for T, I can solve for the temperature difference relative to some reference temperature. And that's always going to give me at least one additional or one homogeneous boundary condition, right? So in this case, if I solve my problem relative to T infinity, then what that's going to do is it's going to set this temperature here equal to 0, and it's actually going to set this fluid temperature here equal to 0. So it may be that by doing a very simple transformation like that, I can avoid having to go through the headache of doing superposition, right? So I'm going to try that first. I'm going to say, let's try to transform this problem just by solving for theta, where theta is T minus T infinity, right? So the temperature elevation above this reference temperature, rather than solving for T. So here's the substitution that I'll make into my original problem. My original problem is shown over here on the left. Now I substitute in T is equal to T infinity plus theta. T infinity is just a constant. So when I do that, I get the same differential equation. Here, at x equals 0, the temperature is T infinity, which means that my temperature difference is 0, right? So that boundary condition became homogeneous, which is nice. Here at x equals w, minus k dt dx became minus k d theta dx, right? The derivative of T infinity is 0. And then this h bar times the temperature minus T infinity is just h bar times theta at x equal w. So actually, if you look at this, this is also homogeneous, right? If I find a solution theta and I multiply that solution by a constant, the constant's going to cancel out on both sides, so it'll still be a solution. And that's what homogeneous means. If I bring all the theta stuff to one side, to the left side, the other side's going to be 0. If I bring all the temperature stuff to the left side over here, I'm going to be left with T infinity. This was not homogeneous. This is homogeneous. Okay, I have a boundary condition at y equals 0. The heat flux equals minus k dt dy. If I plug in T is equal to T infinity plus theta, I get the heat flux is minus k d theta dy. And then finally, this guy up here, temperature at y equals h is Th, which means that the temperature elevation at y equals h is Th minus T infinity. So here's my new problem, right? It's the same problem. I just transformed it to be in terms of theta rather than in terms of T. And when I check my new problem, I see that it's at least gotten closer to being solvable using separation of variables. I have a PDE that's homogeneous, and actually both of these boundary conditions in X are homogeneous. These boundary conditions in Y are not, but they don't have to be, right? I just have to have one direction where both boundary conditions are homogeneous, and in this case it's the x direction. So this now is a problem that I can solve using separation of variables, whereas this original problem I could not. Right? So that's a very easy way to take a real problem and you know, with little effort, turn it into one that you can solve with separation of variables. Okay, so the other thing I'd like to talk about, which we didn't talk about last time, is the Eigen problem that you're going to get when you have a convective boundary condition. So we did a problem last time where the two homogeneous boundary conditions were pretty simple, right? They were just the heat flux, or the temperature gradient was 0, or the temperature is 0. This guy's a little more difficult, right? It's still homogeneous, but it's a little more difficult. And what that's going to do is make your Eigen condition, so the process of finding your eigenvalue is a little bit harder, right? So let's talk about how you deal with that. And the other thing I want to talk about is this situation I have here now where both of my boundary conditions in the non-homogeneous direction are not homogeneous, right? And that's going to require us to use the orthogonality of the eigenfunctions twice, right? So nothing really new here, just kind of digging a little deeper into stuff that we already learned about in the last 2 lectures. Okay, so let's just go through the process of using separation of variables again. So we'll go through the same steps a little faster this time, because hopefully it's now, you know, your second time around. But the steps are, after you've decided you can use separation of variables, then the first step is separate the variables. So here I have this function theta, which is a function of x and y, and I'm going to split it into 2 functions, theta x and theta y. So I do that just through substitution. Right, so I plug in theta x times theta y for theta here. Here I'm taking 2 derivatives in x of these things, and of course theta y is not a function of x, so I pull it out. I pull theta x out of this one. I divide this whole big thing through by theta x times theta y. So here theta y cancels, and here theta x cancels. Then I'm left with this group that's only a function of x, and this group that's only a function of y. And again, if I think about it a little bit, I realize that these 2 things both have to be constant, so they're equal and opposite constants, right? So I've basically split this partial differential equation into 2 ordinary differential equations, right? And the question then is, what are the 2 ordinary differential equations, right? Because I can either choose a positive constant for this one and a negative constant for this one, or vice versa, right? So I can either have you know, d squared theta x dx squared minus lambda squared theta x, or d squared theta x dx squared plus lambda squared theta x, and the opposite over here. And it's important that you don't choose this arbitrarily, right? This choice is guided by me remembering that my homogeneous boundary conditions are in the x direction. So that means I have to get a certain ODE for theta x, and that ODE is this one right here, right? I need to have sines and cosines in the x direction, because those will become my orthogonal eigenfunctions, right? I can't mess that up, or I'm gonna run into a brick wall, you know, 6 steps from now. So this is what I choose. I choose the positive constant here, which means I got to choose the negative constant here, and this becomes my Eigen problem, right? So the next step is solve the Eigen problem. The solution to this is, you know, sine and cosine, so that's easy. In this case, the boundary conditions are at x equals 0, I have 0, and at x equals w, I have this situation where conduction is balancing convection, right? So again, I have to turn these boundary conditions into boundary conditions for theta x, and that's just remembering that theta is theta x times theta y. So here, theta x at x equals 0 times theta y equals 0. I can't have theta y be 0 everywhere, so this just says theta x at x equals 0 is 0. That's my boundary condition for this guy at x equals 0. And then here I have, let's see, minus k d theta dx at x equals w has to be equal to h bar times theta at x equals w. So if I plug in theta is theta x times theta y, then I get this on this side and this on this side. The theta y's cancel, and I'm left with this boundary condition here, at x equals w. So a little bit more interesting boundary condition over at x equals w. Okay, so the steps that we did last time was we took this equation and plugged it into our first boundary condition, and that basically told us what our eigenfunctions look like. And then we took the result and plugged it into our second boundary condition, and that gave us all of our eigenvalues, right? So the same thing will happen in this case. I'm going to take this solution and plug it into this boundary condition. So I evaluated at x equals 0. The sine of 0 is 0. The cosine of 0 is 1. So I'm left here with c2 is equal to 0. So c2 equals 0 gets rid of this part of it. And theta x is c1 times the sine of lambda x. So once again, I know that my eigenfunctions are sine functions, right? That's what this is telling me. The next thing I need is to get all my eigenvalues, these lambdas, right? So I need some condition, my eigen condition, that will give me all of my eigenvalues. So we get that from our other boundary condition. So right here we have our second boundary condition, and we plug in this solution, now with the cosine gone, into this boundary condition. So minus k times the derivative of this is c1 lambda cosine of lambda w, and then h bar times this is h bar times c1 sine of lambda w. So here's my condition, right? My eigenvalues are the roots of this condition. You can see c1 cancels from both sides. So on the left side I'll have minus k lambda over h bar, and on the right side I have sine of lambda w over cosine of lambda w, and sine over cosine is tangent. So here's my eigen condition, right? I need to find eigenvalues that satisfy this condition, and you're always going to find that there's more than just one root to this eigen condition, right? There's a bunch of roots. Last time when we did this, our eigen condition was really simple. It was something like the cosine of lambda w had to be equal to 0, and you could just stare at that and go, oh, okay, I know that cosine is 0 when the argument is pi over 2, and then 3 pi over 2 and 5 pi over 2. So it was really easy to identify all of the roots of that equation, all of the eigenvalues. This one's a little harder, right? I can't just stare at this and identify all of the roots of this equation, but I know that there must be a whole bunch of roots. And I know that because if you think about what tangent does, you know, it sort of repeats itself over and over again. And then what is this over here? Well, this is some kind of a line. So I basically have to figure out the intersection of this line with this function. So let's think about what that looks like. Here I've plotted the right side of this equation and the left side of this equation, right? So the right side of this equation, I'm plotting the tangent of lambda times w. So my x-axis is lambda times w, just because that makes it easier for me to see these intervals, right? So what does the tangent of lambda times w do? Well, the tangent of 0 is 0, and then as lambda times w approaches pi over 2, tangent approaches infinity. As soon as lambda times w gets a little bit above pi over 2, then it goes to minus infinity, right? And then it goes back to 0, and then 3 pi over 2 goes to infinity, and it keeps repeating this pattern over and over again, right? I got sick of plotting it, but this would go on forever. So that's the right side of this condition. What does the left side of this condition look like? So if I plotted the left side of this as a function of lambda w, this is just a line, right? This is a line. The slope is minus k over h bar times w. This is actually 1 over the Biot number. So this is a line with a slope that looks like this. So where are my eigenvalues then? Well, my eigenvalues occur every time the left side and the right side are equal. So every time this line intersects these tangents, I get an eigenvalue, right? So my first eigenvalue is actually 0. They intersect here, but that's not very helpful because the sine of 0 is 0 and it doesn't add anything to my solution. So I'm going to throw that one away. So the first one I'm actually going to consider is this guy here. So this is my first eigenvalue. It's the intersection of this line and this tangent function in this interval, right? And then if I keep going, I find my second eigenvalue. So it's the intersection of those same two things, but in this interval. And then there'd be another one in this interval, and so on and so forth. So there are an infinite number of eigenvalues, right? I can get as many of these as I choose to get just by continuing to move out to bigger and bigger lambda w's. They're just a little bit more difficult to identify than they were when it was just cosine of lambda w equals 0. Right? So it's really, at this point, just a math problem, and a math problem of just finding repeated roots of an equation, right? And then every different software you want to pick up is going to have its own way of doing this. So we're going to look at how you do this in ease. I think the book talks about how you might do it in MATLAB too, because MATLAB has these great root finding, bounded root finding techniques. But you know, there's all different ways of doing it. The real trick of it is just identifying what range of values to look in to find each of your eigenvalues, right? So if you look at this, I can see right away, just from the shape of these curves, that this first eigenvalue is going to fall between pi over 2 and pi, right? So I know where to look for that first eigenvalue. And the second eigenvalue is going to fall between 3 pi over 2 and 2 pi, right? So I know where to look for the second one. And the third one's going to be between 5 pi over 2 and 3 pi, right? So I've identified these ranges. In general, the ith eigenvalue is going to fall between this number and this number. And that's really all I need. As long as I know where to look, it's really easy to program a software to go find a root in that range, right? If you don't know where to look, then it gets a lot harder, because your software is likely to go find one root and then not know where to go to find the next one and the next one and the next one, right? But these are the ranges that we will look in. And we'll use ease to find each of these roots.